All right, guys, so the second lesson is going to be on power and efficiency. Again, this is something that we already talked about. Just want to kind of go over this again. So again, power is simply the rate of doing work. And we saw this in our Stairmaster lab, right? And in order to kind of calculate the power that you are using in going up the stairs, right, we use this formula of power equals work divided by time, which we could also define as the change in energy divided by time. And our units that we're typically going to use for power is watts. So a few example problems here. You can pause the video to go ahead and solve those. I'm just going to go straight through and solve them. So pause and then unpause when you've gone through these problems. All right. So for this first one, we have a physics student. He's going to body slam a biology student, as he should, or as they should. So he lifts a 75-kilogram student over his head, 2.2 meters in 0.675 seconds. How much power did they generate? So again, in this case, a little bit difficult for us to calculate force. All right, so we're not necessarily going to be able to use work, but what we can do is we can look at the change in energy divided by time. Right, in this case, because they're lifting them up, right, they're moving them against gravity, so we can use the change in potential energy divided by time. We have the mass, we know gravity, and then we're given the height. Divide that all by the time. And then we end up with a power of 2,400 watts. All right. Our second problem here, we have an open sleigh. All right. Teacher cracks a whip, speeds up to 12 meters a second in 4.5 seconds. Sleigh has a mass of 850 kilograms. How much power did it generate? And again, friction in this case is negligible. Right. So once again, use a different color. We don't know force, so instead of using work, right, we can look at the change in energy over time. In this case, because this is an object in motion, we can look at the change in kinetic energy. So 1/2 mass times the change in velocity squared divided by time. Okay, expand that out. 1/2 mass initial velocity minus, final velocity minus initial velocity squared, all divided by time. Plug in the numbers we know. Mass is 850. We have our final velocity minus our initial velocity. Square both of those. Again, that's an area where you can go wrong. Calculate that all out. End up with 12,000 watts. So we can derive another formula, and we did this previously. Just wanted to go over that again, right? We know that power is work divided by time. Again, if we expand out work, we know that that is also force times distance divided by time. And then we know that distance divided by time is velocity, which means that power is also equal to force times velocity. Now, keep in mind, this is only true when velocity is constant. All right, so keep that in mind. If velocity is changing, we cannot use that formula. All right, so one more example here. All right, we have a student pushing their physics homework up a 40-degree ramp at a constant velocity of 3.2 meters per second. We're given a frictional force. How much power must a student exert? All right, so in this case, we know that power is going to be equal to their force applied times the velocity. Now in this case, because it's moving at constant velocity, we know that the net force is equal to 0, which means that the force applied is equal to the force of gravity parallel plus force of friction. All right, because again, if we kind of break this out into a free body diagram, we see F applied, F friction, F gravity, F gravity perpendicular, F in the x direction, or F parallel. So anyways, what we end up with here is our x component of gravity plus force of friction. So we expand that out. That means force of gravity x direction is going to be mass gravity sine our angle, which is 40, plus 26 newtons, which is our friction. Okay. And all that times velocity, which is 3.2. Power, we get 410 kilograms meters per second. Okay, for machine, couple of numbers here to know. Electric heater, right, converting electricity into heat is about 95% efficient, right? Only 5% of the energy is being lost. A car, right, we lose a lot of our power to friction and thermal energy, 30%. And a light bulb, and this is talking about like old school light bulbs, are going to be 3% efficient. Those are like, again, old incandescent light bulbs. So once again, our efficiency formula is the work out divided by work in times 100. Okay, which is going to be the same as power in divided by power out times 100. Again, expressed as a ratio, not a percentage. Moving on. Most common source of our confusion when calculating this efficiency is understanding which value applies to work in or work out. So the work or power in is going to be our total energy or power used by the process. And the work power out is what was actually being accomplished by the process. So keep in mind, no machine is going to be 100% efficient. Unfortunately, if they were, right, we can get some perpetual motion machines. So our work in is always going to be greater than our work out. And our efficiency is always going to be equal to or less than 100%. Oops, sorry. Got that on the wrong side. All right. Good time to pause. We're going to go through a few example problems, and then that will be kind of wrapping up this lesson. So we can unpause when you're ready. Okay, for this first one, I have a little dragster going here. I'm just going to visualize what's going on in this problem. So we have it accelerating in this direction. We know the mass of our cart is 2,800 kilograms. The height is going to be 120 as it goes up a vertical 90% vertical curve. There should be. There, 90. All right, so our first step is calculating minimum amount of work done on the car in order for it to reach its peak. So again, when we're talking about work, we can apply force and distance, although in this case, not as known, but we also can look at the change in energy, and we do know mass, gravity, and height. So in this case, work is going to be the mass, 2,800, times gravity, times our height. And so our theoretical work done is going to be about, let's say, 3.3 times 10 to the 6th power joules. All right. We do have some reality, though, right? It's accelerated from 0 to 193 kilometers an hour in 3.8 seconds. We can convert that. So you don't need to memorize this, but it is helpful. A conversion from kilometers per hour to meters per second is just going to be multiply it by 3.6. We're going to get 53.61 meters per second. Okay, then there we have our work equals change in energy. Because in this case we are in motion, we can look at it as the change in kinetic energy. So we have 1/2 mass times change in velocity squared. Plug in our numbers. Don't forget to square your velocity. And then we get 4024000 joules. All right. So notice not the same number. Still need to find the power input. Change. All right. So I know that power input is going to be our work divided by our time. So number we just got divided by our time, which was 3.8 seconds. We got 1.06 to 10th power watts. Okay, now we're looking at efficiency. All right, what's our work output divided by our work input times 100. So as we said, 3.3 times 10 to the 6 divided by 4.02 times 10 to the 6 multiply that all by 100. Equals about 82%. Okay. Second coaster. All right, so we have launched up a hill 34 meters high, traveling 0 to 64 in 2 seconds. Full car has mass. Okay, I'm going to just draw out my little roller coaster. Okay. So key thing here is the max height, 34 meters. Now I'm just going to finish out this track. Ooh. 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 All right. So, finishing out my cart here. So my mass is 4,500 kilograms. All right, my let's see, final velocity is, let's see, 17.78 meters per second. I feel like I did something. Sorry. Realize I made calculation error somewhere. Sorry. Yeah, I realized. Sorry, over here. I did it right. I just mentioned something wrong. Right. Sorry. To convert from kilometers per hour to meters per second, it's not timesing by 3.6. It's dividing. So just kind of keep that in mind. So 64 kilometers per hour to get that in meters per second divided by 3.6. All right, that's where I'm getting this. All right, so have my track. Again, you could really draw this however you wanted. The key thing is that the max height is 34 meters. All right, so now I want to find the power output of the ride. First step is I need to find how much work kind of came out. All right, so for my work, right, I'm looking for my change in energy. Right, so, right, my total energy is going to be kinetic plus potential. Right. Now, my kinetic. All right, if I just plug all my formulas in, I know this is going to be 1.499 times 10 to the 6 plus 7.11 times 10 to the 6th, which gives me 2.2 times 10 to the 6th. All right. Again, if you want to know how I got this, I just kind of skipped ahead. Right, I know that my change in potential was just mass gravity height, right, which was 4,500, 9.8, 34. That's where I'm getting the 1.499 times 10 to the 6th. My change in kinetic, mass final velocity squared is 1/2 4,500 times the velocity squared. All right. So that's where I'm getting that. A put those together right at the beginning first. If you need a reminder of how to get those numbers, that's how it was. All right. Calculate my power. 2.2 times 10 to the 6 joules divided by 2 seconds equals 1.105 times 10 to the 6th watts. Okay, now I find the efficiency. Okay, what's my power output divided by my power input? All right, so power output, 1.105 times 10 to the 6. All right, and we're given the power input is 1.45 megawatts. All right, so think about what does the prefix mega mean? We're going to end up with 10 to the 6, all times 100. Okay, my efficiency is about 76%. Okay, see, if car pulls in a station at 8 meters per second, how much heat has been generated from the first peak? Okay. Or it could be since the first peak. So, in a perfect world, right, change in energy is 0, right? And I know that my initial energy is my kinetic energy plus my thermal energy. All right, another way to say that is my thermal energy is going to be my initial energy minus my kinetic energy, final kinetic energy. So I know that my thermal energy will equal, what did I get earlier? Okay, so 2.2 times 10 to the 6th power minus my final kinetic, which is 1/2. Mass is 9,500. It's giving me velocity 8 squared. Right. And then my thermal energy output is going to be 2.07 times 10 to the 6th power joules. Okay, finally brought to rest over a distance of 2 meters. How much force is required? Put this all out. Let's solve for my net force, because that's what it's asking for. All right, another way I can expand this out. We know that my final kinetic minus my initial kinetic, that's the change in kinetic energy, divided by D. Okay, it's equal to negative 1/2 mass velocity squared divided by D. Plug in the numbers I know. Okay, and my net force is going to be negative, indicating the direction, 7,200 newtons. The next lesson is going to get into momentum and collisions, and that's all going to be new.